Welcome to the video for the final question on the example exam. In this one, we'll solve for the reactions of an indeterminate structure that we have already solved for the deflection at one of the points that have support. Next, we want to know what the reaction will be at point A if we have a pinned reaction there to supply a force in the y direction with the same load. We've already determined what the deflection would be like if we had this loading without the pin. And we can break this into two systems, right? This one and this one. So we know that the deflection caused by these two has to sum to 0. And we know what it is for this one already. It's negative 3,666 2/3 kip feet cubed divided by the Young's modulus and the second moment of inertia, which will of course be the same in both these systems. So when we're looking at this system, we can sort of immediately have our shear. It's going to be a constant AY. Whatever the reaction is at A, whatever this fictitious force is at A, upward. Our moment is the integral of that. It's going to be AY times X plus some constant of integration C5. But of course we have a boundary condition at A, and that boundary condition is that the moment at A, or at X equals 0, better equal 0. Because, well, it's a free end. If it's a free end, there's no inside for there to be internal moment. And so from there we can go to the rotation. The rotation times EI is the integral of the moment. We said that C5 was 0, so it becomes AY times X squared divided by 2 plus some constant of integration C6. Now this one, we do have a boundary condition, but that boundary condition isn't at A. Just like last time, the boundary condition is that at point B, or X equals 10 feet, the rotation has to equal 0. So that means we need to plug 10 into there and find out what C6 is. If we do that, we're going to find AY times 50 minus C6 equals 0 gives us that C6 equals negative 50 times AY. That's should be intuitive for you. If we're pushing this up, the slope at point A has to be negative as we get there. And now we have our deflection equation. So the deflection is going to be the integral of this. So keep multiplying everything by the Young's modulus and the second moment of inertia. No reason not to do that. We end up with AY X cubed over 6 plus minus 50 AY x plus some constant of integration C7. Now, when we do this, we have a boundary condition, right? We have a boundary condition. That boundary condition is that the deflection at point B, or the deflection at x equals 10 feet, that has to equal 0 because we got a fixed end right there. So that tells us that we have AY 1000 over 6 minus 500 AY plus C7 equals 0, and that's going to give us C7, which is going to be where do I put that? C7 is going to equal the deflection at 0, and that's going to be positive AY times 1000 thirds. So, to find out what the reaction AY is, we need to set the summation of deflections at A to 0, and that's going to mean that we can write 0 is equal to negative 3.66662 thirds plus AY times 1000 thirds. Solving that all out, we're going to get reaction AY is equal to positive 11 kips. All right. Don't forget how to do our indeterminate structures, because this has one more reaction that we can solve using our static equations of equilibrium.